Methylene blue is an incredibly powerful drug also in cancer. It's hailed as a magical savior by some, but derided as an absolute sham by others. And as usual, the truth is somewhere in between. Because whilst it is helpful in quite a lot of applications, it has some undesirable side effects which impacts its long-term usability. Now, cancer is a chronic illness, so effectively treating cancer requires a long-term course of treatment with as little side effects as possible to sustain treatment over years. And of course, this brings us to the question whether we can get the positive effects of methylene blue without the negative side effects, so we can indeed use these positive effects long-term to help cancer patients live longer. The perhaps surprising answer to that is yes, but to understand how we can do this, we must first understand what methylene does, how it does it, and then how we may replace it. So let's do just that. If you don't know who I am, my name is Merlin. I'm working on my master's degree in molecular biotech, and I'm a co-founder of Marchwood, where we try to eradicate cancer as a cause of death. If you want to learn more about what we do, you can go to marchwood.com/outlive. With that out of the way, let's get into the video. As I said at the start, methylene is quite the powerful drug. But to understand why we might not want to use it chronically, we first need to understand what it actually does pharmacologically. So if we here have, I'm going to abbreviate it, methylene blue. It does a few things for us. Methylene blue, when administered to patients, will categorically suppress a compound, or the generation of a compound that is known as nitric oxide. I'll shorten it to NO. It will also categorically suppress the enzyme known as guanylate cyclase. So it will suppress this guanylate late cyclase. I could have shortened that as well. And it will categorically inhibit another enzyme which is known as monoamine oxidase. These are the three principal things that methylene blue does, and we'll go over each of these things one by one so you can appreciate why that might be a bad thing. So let's look at nitric oxide so we can understand why suppressing it categorically might be a bad idea. If we go over and we have our nitric oxide, this nitric oxide will have a few different functions within our body. One of the ways in which it is used in our body is in immune signaling. And it is used here in a lot of different contexts, which means that suppressing or promoting nitric oxide production will have incredibly varied effects depending on the specific context. And this also varies within different cancer patients. So if we have different cancers, the categorical suppression of nitric oxide will have differing effects, even within the same kind of cluster of diseases. Now, another thing that nitric oxide does is that it regulates blood pressure, or it's used in the regulation of blood pressure. So obviously this means that if we categorically suppress nitric oxide, we will change how our body regulates blood pressure. And in fact, nitric oxide is used specifically to relax the musculature on artery walls. And obviously, if you cannot relax the musculature on artery walls, then you will have a problem with hypertension. You will actually get higher blood pressure. And this is, of course, a problem because higher blood pressure creates risk for a lot of downstream diseases that we do not want. So again, this is kind of a thing that goes against the chronic application of this methylene blue because it dysregulates by chronic application blood pressure. And the third thing that nitric oxide does is that it improves the activity of what is known as the Fas I'm going to shorten it, death receptor. That's a pretty metal name, fast death receptor, but what the fast death receptor actually does is it transmits signals from specialized immune cells that are supposed to kill cancer cells. So this fast death receptor is the docking point for immune cells to kill cancer cells and also other cell types. And there are other death receptors as well. This is only one of them, but nitric oxide improves the function of the fast death receptor. So again, suppressing it might be not a good idea in cancer patients, as this fast death receptor is one of the ways in which the body can actually fight cancer cells by killing cancer cells, at least as long as the cancer cells still have fast death receptor, which is a different issue of cancer being kind of a disease of evolution, which we will go over in a future video. So now, having understood the function of nitric oxide, we can understand why it is perhaps not a good idea to categorically suppress it, especially long term. And this, of course, makes methylene blue kind of questionable, especially in chronic use. Let's look at the next thing, the suppression of guanylate cyclase. Now, if we look at what guanylate cyclase does, it's actually similarly ubiquitous as nitric oxide. It's just on a more cell internal level. So guanylate cyclase is actually used in a lot of different cell signaling, or specifically cell internal signaling pathways. And it's not just used in like one kind of pathway, but it's used in various different pathways across different cell types. Which means that whilst we might not know exactly what its effects are in all cell types, just categorically suppressing its function is not ideal, right? Because if we have a lot of different cell types that all depend on this guanylate cyclase to properly function, let's say we have an immune cell here, a macrophage for example, we have a striated myocyte here, and we have, let's say we have a neuron, right? And they all use this to propagate cell internal signals, and we just suppress its function. It can have disastrous effects in these cells, or it could have good effects, we just don't know. And even if it has a good effect in one cell type, it can have disastrous effects in other cell types, because these cell types will use the same kind of archetypal signaling pathways, but use them with different start and end points. So basically with different external signals, cell external signals that activate these pathways, and then different results that are triggered by that pathway at the end. But they will still use guanylate cyclase to transmit the signal at some point, at least in a lot of cell types. So again, this shows us that the categorical suppression here of guanylate cyclase probably not a good idea, especially again in the chronic context. Now, in acute context where you have a patient where it acutely helps them to give them methylene blue, perhaps not so questionable. But in chronic application, maybe not a good idea. Okay, let's look at the third point of what nitric oxide does, because this might be more problematic than you would think. And it is that problematic because monoamine oxidase is used in the recycling of certain neurotransmitters. Specifically, it's used in recycling of serotonin and dopamine, for example. Now, if you have someone who has taken methylene blue, what they will oftentimes say is that they take methylene blue, they just feel more awake and more alert and just more energized. And if methylene blue actually did that for them in a mechanistic, basic way of giving them just more available energy, that would be splendid. But what methylene blue does through inhibiting monoamine oxidase is that it inhibits the recycling of the serotonin and dopamine, and this has downstream effects. because serotonin and dopamine signaling is the kind of awake, energetic, happy, feel good kind of signaling. It's not purely feel good, but it's also what drives you forward to, or compels you to do an action where you expect a reward in the future, especially the dopamine part. It's the reason why you would, for example, do difficult sports, intense sports that's not necessarily pleasurable in the moment, but you know that after the sports you will feel good about it, and that's the dopaminergic system there pushing you through the sports unit to actually propel you to the nice reward at the end of the sports session, even though the sports session might not be that rewarding in and of itself because it's arduous. And what this does is that it makes you feel energized without necessarily energizing you. You feel energized, right? And you feeling energized is perhaps not bad, right? And you would say that's perhaps a good thing. And perhaps yes, perhaps no. In chronic use, it's kind of a thing where you would then just develop a habit of using it, and over time your body would adapt to normalize your recycling of serotonin and dopamine, which would take away this effect again, and you would need to up the dose to feel the same amount of good with methylene blue use. So it's kind of like a drug, and in fact there are amphetamines that actually use this mechanism of interfering with the recycling of dopamine and serotonin to improve the positive feeling action of these amphetamines. And I think that kind of shows why it might be a bad idea to use methylene blue here chronically. Again, I think in acute application, methylene blue is incredibly powerful. And I think in cases where we cannot get the same effects of methylene blue by other means, it might be necessary. But to take it categorically across the board to in patients that might not need it, I don't think is necessarily smart. And that being said, the inhibition of monoamine oxidase is perhaps not the most killer argument, but as you have already seen with the categorical suppression of nitric oxide and the categorical suppression of guanylate cyclase, the chronic application of methylene blue has a few more risks than we perhaps would like. Okay, so methylene blue is just a bad thing, a bad deal. We shouldn't be using it. I stated multiple times that it's good for acute use. So what actually is it good for? Why would we even want to use it? Because thus far, it kind of seems like, it's bad, right? It actually isn't. Because by suppressing nitric oxide categorically, one of the things it does is that it also suppresses the negative effects of nitric oxide for cancer. So it doesn't just suppress nitric oxide effects, or the positive nitric oxide effects for cancer patients, it also suppresses the negative effects of nitric oxide for cancer patients. Okay, that's a good part. Another thing it does is that it actually does mechanistically, and this is what I kind of alluded to in the monoamine oxidase case, it actually mechanistically improves mitochondrial function, or mitochondrial capability of mitochondria to produce energy. Chondrial function, right? And this is a very, 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 very good thing for a cancer patient, because a lot of cancers are mitochondrially negatively impact. Their mitochondria don't work properly, and that has a few consequences for energy metabolism within the cell, for genome stability, for apoptotic resistance, which is basically resistance of the cancer cell toward death. And of course, if it has less apoptotic resistance, it is more likely to die, which is actually exactly what we want in cancer patients. cancer cells that are more likely to die. Okay, so we have these two effects here that are kind of, or not just kind of, that are, positive in what methylene blue does. But we have these three things here that we might not want to have. So let's actually look at how we might suppress the negative effects of nitric oxides and mechanistically improve mitochondrial function by other means without relying on methylene blue. But before we get into this, if you want to read the full article on this topic, on methylene blue and nitric oxide and how they interrelate, you can find a link in the description below. It goes into way more detail than I can here, and also way more technical detail, so if that interests you, check it out. Okay, so let's look at exactly how we can prevent the negative effects of nitric oxide for cancer patients, right? So we have nitric oxide's negative effects. So I would say negative effects of nitric oxide. And these are mainly propagated in two ways. One of these is via nitric oxide itself. And that has to do with immune signaling, which is context dependent. So in some contexts, having nitric oxide signaling is perhaps less than ideal for the cancer patients. In some contexts, it's going to be ideal for the cancer patients. And we simply cannot do anything about that unless we know very, very specifically what the context is for the specific cancer patients. So this part we don't really want to attack unless we have a very, very specific clinical case. The second way in which this negative effect of nitric oxide gets transmitted is by the oxidization of nitric oxide to what is known as peroxynitride, which is a radical, and radicals in general in chemistry are highly reactive, and peroxynitride is actually one of the two most reactive biologic or biochemically active radicals. And it is about 20 times as reactive as something like hydrogen peroxide, which a lot of you know as a powerful oxidant and bleaching agent. So very, very reactive, this peroxynitride. And this we can actually do something against. So peroxynitride is generated when nitric oxide comes into contact with superoxide anions. And these two react to form peroxynitride. Now, obviously, we can limit the production of peroxynitride if we lower nitric oxide, which is something that methylene blue would do. We kind of don't want that. We discussed why we don't want that categorically. In certain clinical cases, yes, sure, we do want that, but we also have other levers. We can, for example, just minimize the availability of this superoxide anion. And we can also, this is written incorrectly, we can also kind of scavenge this away by just directly, reacting it off with certain compounds that our body can use. Spoiler, it's antioxidants. And by scavenging this peroxynitride, it cannot damage certain important structures, cannot damage the genome, cannot damage the mitochondria, because we have scavenged it before it can wreak that damage. So these two things, right? Lowering of the superoxide anion state and also removing of peroxynitride. These two things we can actually do something about. I already kind of spoiled that to do this, we can use antioxidants. Now, specifically what I mean with using antioxidants, not supplementing antioxidants, but actually enabling your cells to produce the appropriate antioxidants to neutralize these things. And the most important antioxidant that our body uses is what is known as glutathione. And this glutathione can be used by the body to do exactly this. Okay, how do we ensure that glutathione is produced adequately? For that, we need to do two things. We need to provide the body with the basic building blocks of glutathione, which in this case is protein and sulfur. And we need to supply the body or keep the body in a metabolic state in which it actually recycles glutathione that has been used up. So glutathione that has been used to reduce or antioxidize these compounds up here, to reactivate it, to make it, or to enable it to again antioxidize these highly oxidative compounds. So we need to engender recycling. Well, how do we do that? Okay, so protein is pretty much easy. You just eat protein. You don't need to go overboard. You just need to have a healthy supply of protein. That means that you need to have some protein in your diet. Best when it comes from animal proteins, because we are animals. We kind of just use animal proteins best. If it's plant proteins, there are some caveats there. You can find that on our website. But anyway, and the other thing you need is sulfur. Now, sulfur is mainly found in two specific amino acids, and amino acids are a constituent part of proteins. And sulfur specifically is found in the amino acids cysteine and methionine. And these two compounds are found a lot in eggs and meats and various animal products, and also cereals. Now, cereals I don't recommend for various reasons. Again, you can find it on the website, completely, openly accessible. But cysteine and methionine, mostly from eggs, meats, and other animal products. And if you eat those, you probably do have enough sulfur to synthesize enough glutathione. So far, so good. So how do we engender this recycling? How do we make glutathione, or make our body recycle glutathione, or perhaps enable it to recycle it more efficiently? For this, we actually want to improve mitochondrial metabolism. We want to use mitochondrial metabolism as much as possible. And why do we want to do this? Because it's actually the mitochondria that keep this recycling of glutathione up. So it's actually the mitochondria that recycle glutathione and provide the body, or the cell rather, with enough glutathione to do these reductive or antioxidant reactions. Now we get into exactly how we can do this in just a bit when we talk about how to do the second part of what methylene blue can do without methylene blue. But before that, there's another thing we can do to actually scavenge these peroxynitrite by using a more ubiquitous antioxidant. Now, you might think because peroxynitrite is a very powerful oxidative agent, that we would need a very powerful reductive or antioxidative agent to neutralize it. Actually, the opposite is true, because it being a very, very powerful oxidative agent means that it is highly reactive, which is also where its danger comes from, right? So this one is highly reactive, which means it will react with basically anything. So if we supply the environment around this peroxynitrite with something that can reduce it or antioxidize it, but doesn't reduce or antioxidize any of the other kind of reactive oxygen species or oxidants in our system, like nitric oxide itself. Nitric oxide itself is a oxidative agent, but it is less reactive than peroxynitrite. And in contrast to peroxynitrite, we actually want nitric oxide to function well and to not be antioxidized or reduced, so that it can unfold its signaling properly. And we can actually then specifically attack this up here, this highly reactive nature of peroxynitrite, by supplying it with a very weak reductive agent. So specifically not just hydrogen, but aqueous hydrogen, dissolved in water, this hydrogen will not react with this. It just can't. It's too inert. It's highly inert. It doesn't like reacting that much, at least in this specific context. Now, granted, if you make a hydrogen-oxygen mixture and set it on fire, it's going to go boom. So it is reactive in certain contexts, but again, as I said, you need the oxygen for that, and you don't need to have it in, small concentrations within liquid solution. It doesn't do anything there. So it won't react with a nitric oxide. It will, however, react freely with this highly reactive peroxynitride, and it will neutralize it. It will just eliminate it. And then you don't have peroxynitride, which is, again, one of the ways by which the negative effects of nitric oxide for cancer patients is actually promulgated. So having this hydrogen is a very powerful tool. Of course, just having proper antioxidant function by having proper mitochondrial health and proper nutrition so you can synthesize and recycle glutathione appropriately is already a very, 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 very good step. But if you want to supercharge it, you can use this elemental hydrogen dissolved in water. And you might now say, okay, sounds fancy, cool. I want, this hydrogen dissolved in water. How on earth do I do that? How on earth do I get my hands on hydrogen dissolved in water? Simple. There's actually firms that make bottles, it's kind of electrolytic devices that are formed like bottles, and these electrolytic devices will electrolyze water. So they will take water from the tap, for example, and they will electrolyze it and give you your hydrogen and half of an elemental oxygen. And they will vent that elemental oxygen out, or the oxygen will land in the water. It doesn't really matter for our purposes because the hydrogen and oxygen in aqueous solution won't really react with each other. Now, in some contexts, when you kind of pre-activate the oxygen, they might react in aqueous solution at the concentrations they're at in these hydrogen or in these electrolytic devices, in these bottles. That won't really happen, and the hydrogen makes it into your system, makes it all the way to the peroxynitride to neutralize it. Very cool, very powerful tool. You can get it. They're relatively price efficient and cheap on the free market. Just make sure that it's actually a electrolytic generator that works, that actually infuses your water with enough hydrogen to be clinically effective. Because I've seen some that we make hydrogenated water, and it turns then out that yes, technically true, but the concentration that they achieve of hydrogen in the water is just subpar and doesn't, it's too expensive for the low amount of hydrogen that it gets into the water. So be aware of that. But very, very powerful tool to, again, eliminate more of the negative effects of nitric oxide. With peroxynitride dealt with kind of one half of the negative effects of nitric oxide dealt with, the one half that we actually can deal with, we now, of course, want to look at how we can improve mitochondrial function and mitochondrial metabolism for two reasons: to more efficiently recycle glutathione and to emulate the effects, the pharmacological positive effects of methylene blue. That was the goal from the get-go. By the way, everything I'm about to talk about with improving mitochondrial function is written out in great detail in our Mosaic Method guide that you can access completely for free at marshall.com/mosaic. If you want to get a leg up on cancer, which I suspect you very much want to do, because who wouldn't, go check it out. It's absolutely worth it. Improving our mitochondrial function is actually far more simple than you may expect. Now, there's a lot of ways in which we can do it, but today I want to focus more on the ways that we can do so by diet, by adapting our diet and metabolism in a way that supports mitochondrial function instead of destroying it. Now, mitochondria are oftentimes called the powerhouses of the cell. And whilst this is kind of true, it is incomplete because these mitochondria are only part of the cell's energy metabolism. Specifically, they are the oxidative part. This is kind of a bit of a simplification, but it is 99% true. Oxidative part of energy metabolism. And these are the mitochondria or mitochondria. And they are oftentimes known as, or rather this is one mitochondrion, and they're oftentimes called the powerhouses of the cell because they do produce the most energy for the cells because they're simply that good at doing it. They're very efficient, both fuel and waste product efficient. They use oxidative metabolism, oxidative energy production, and that, just completely burns the fuel and leaves only CO2 and water as waste, which is very, very efficient. But there is another part of energy metabolism that our cells can use, or another style of energy metabolism that our cells can use, which the cells use. This is a cell, this is the nucleus, and this here is the cytosol. And in the cytosol, our cells actually have the capability of performing fermentation. Specifically sugar fermentation for our cells. Our cells in their cytosol can just generally ferment sugar. And this is, for example, what your muscle cells do when you're doing sprints and you get the lactate stiffness after the sprint where your muscles cramp up and lock up. That is basically the result of the fermentation where your muscle cells fermented sugar into lactate. That lactate is acidic. That acidity negatively impacts your muscle function, and thus the muscles lock up. So we have these two energy production methods. So mitochondria, whilst they produce the most energy in the cell, they're not the only way a cell can produce energy. So yes, kind of powers of the cell, but not categorically exclusively. Now, if you've paid attention, you may already see a kind of picture forming of how we can support mitochondrial energy metabolism. Of course, one way in which we can improve mitochondrial metabolism is by enforcing our cells to rely on mitochondria for energy production. Right? If we can take this fermentation away, the cytosolic fermentation of cells, if we can stop that, then we can indeed improve mitochondrial function and mitochondrial metabolism just by forcing the cells to use mitochondria for energy production. How would we do that? Well, if you've paid attention, I said that our cells specifically ferment sugar. So our cells need sugar to ferment. So if we want to stop fermentation, we can stop the supply of sugar. That's easier said than done because, we have blood sugar. Our body, or our liver specifically, actually produces or generates constant sugar to keep that sugar in our blood so that our red blood cells, which actually don't have mitochondria, can actually survive long enough and fulfill their functions to act as oxygen transporters in our blood. Good. But we don't want other cells to use that sugar. We just need our red blood cells to use that sugar, and other cells shouldn't be using it. Makes it easier for everyone. So what we can do is eliminate as much of these sugar spikes as possible, right? So our blood sugar adapts to what we eat. If we don't eat any sugar, we will have or any carbohydrates, we'll have a very, very stable blood sugar. So our blood sugar, this is time, this is sugar concentration. If we don't eat any carbohydrates, this is how our blood sugar will look. It's going to be very stable. Now, we cannot necessarily lower it because we need a certain amount of blood sugar in our blood to fuel our red blood cells, which don't have mitochondria. But we can eliminate some of this sugar availability for example, for cancer cells or other cells that would then limit fermentation if we abstain from carbs. Because if we eat a lot of carbs, then our sugar levels will look more like this. And you can see that the area under the curve on the second here has a lot of area above what the first example has, right? And it might not be that extreme, right? It's kind of, this is more qualitative, but qualitatively it is accurate. So again, improving mitochondrial function, one of the steps of doing that is to go on a ketogenic diet, or that means a diet that is very low in carbohydrates. Another thing we can do, obviously, or that we then need to do, is if we don't eat sugar or carbohydrates as fuel, we need energy from somewhere else. So we will eat fat. Why? Because fat is actually exclusively metabolized in the mitochondria. So sugar, all sugar, whether you actually then burn it completely or whether you ferment it, is first fermented and then the fermentation waste is burnt, right? So sugar has two stages. When you have sugar, it's first fermented, and then the waste of that is fed to the mitochondria, and the mitochondria then burn the waste of the sugar fermentation. If you take fat, that's not how it works. When a cell gets fat, the fat is immediately shipped into the mitochondria, and the mitochondria will then burn the fat completely, gone. Another fuel we can use is something known as ketones. Now, ketones, similarly to fat, they will immediately be shipped to the mitochondria. The mitochondria will burn them completely. They do not have anything to do with fermentation. They cannot be fermented by our bodies. Now, there are some organisms that could ferment fat and ketones. Our cells just can't. So they're burnt to the mitochondria. Now, ketones is not something we eat externally. So we don't really eat ketones in our diet. Now, ketones are present in some of the animal fats that we would eat, but they're not a major part of diet. Fat is, however. And interestingly, our liver will produce ketones from fat to make it easier for cells to generate energy, because ketones are more, let's say ketones, you need to invest less energy up front for ketones to be burnt. And you also don't get as much as from fat, but it's quicker energy than fat. So our liver, once we don't have that unstable blood sugar, once we get a stable blood sugar, our liver will then produce ketones to give our cells much more quicker oxidative energy than the more slow fat-derived oxidative energy. And once we are in ketosis, our mitochondria all throughout the body will actually use both ketones and fat for energy production, kind of use fat as the base load energy production and ketones as the kind of variable load for when you do sports versus when you sleep. You will use less energy when you sleep versus when you're doing high intensity sports. Makes sense, right? So that is the primary kind of dietary metabolic adaptation that we can make to improve mitochondrial function. Now, obviously, mitochondria, like anything in our body, needs certain key nutrients, certain essential nutrients that without these nutrients, mitochondria just don't work. And for mitochondria, these nutrients are specifically iron, copper, various vitamins, and sulfur. Which sulfur we talked about before. Now, sulfur is important not just for glutathione production and recycling, but specifically for parts of the enzymes that actually do this oxidative part of energy metabolism. So this oxidative part of energy metabolism is called oxidative phosphorylation, and then you have the electron transport chain, and in the electron transport chain you have a functional unit that is called iron-sulfur clusters, and these iron-sulfur clusters obviously need sulfur and need iron to be produced because they're iron-sulfur clusters. So having proper nutrition there in terms of iron, in terms of copper, in terms of different vitamins, in terms of sulfur is highly important for mitochondrial health. And doing all of these things will probably improve your mitochondrial health more than taking some methylene blue ever could. And the cool part about this you can do for the rest of your life. This can just be how you eat. Now, granted, that would make you never eat cake again or never eat sweets again, which is perhaps extreme, but I think it's better than dying sooner as a cancer patient. And then also, obviously, caveat, you don't need to never eat cake again. You just need to do it seldomly as a kind of, sweet treat here and there instead of every day. And then, of course, the last part is kind of self-obvious. We need to limit mitochondrial toxins, right? Everything that can damage our mitochondria is not ideal. So smoking is not ideal, alcohol is not ideal, high loads of dietary oxalates is not ideal, high loads of prolamins and lectins are not ideal. Now, prolamins and lectins don't directly affect our mitochondria negatively, but they indirectly affect our mitochondria negatively by promoting chronic inflammation, which kind of chronic inflammation and mitochondrial dysfunction go hand in hand and kind of improve each other, or rather worsen each other. So we need to, or we want to stop that. We want to get rid of those poisons. It's kind of self-evident why we would want that. Now, oxalates, for example, are very common in a lot of plant foods. They don't occur in animal foods or in animal-sourced foods. They exclusively occur in plant foods, and they exist in various concentrations in different plant foods. That's a long list you would have to make, and I don't want to go over that here in depth. And then you have prolamins and lectins, which are found in cereals and legumes respectively, and that is also why I said that yes, technically sulfur is accessible from cereals, but because cereals have prolamin, which is negative for mitochondrial health, I wouldn't recommend getting your sulfur from cereals, but rather from eggs and meat, right? I think that makes sense. And I think that gets us to the end. So we looked at the pharmacological effects of methylene blue, which is the suppression of nitric oxide, the suppression of guanylate cyclase, and the inhibition of monoamine oxidase. Now, nitric oxide suppression categorically was banned because it's used in both in the relaxation of artery walls, which would then, if you suppress it, give you high blood pressure, and it's used in immune signaling, which is highly context dependent, and categorical suppression there just runs into a lot of issues. Guanylate cyclase is a bit similar in that it is used in a lot of cells. So suppressing guanylate cyclase will disturb certain cell internal signaling pathways, which is also can have a wide array of different consequences that we might not want to deal with. And then, of course, we looked at how we can replicate the positive effects of methylene blue, which specifically are the improvement of mitochondrial function and the removal or the kind of lowering of the negative effects of nitric oxides for cancer patients. And we can improve the negative, or we can kind of buffer the negative effects of nitric oxide for cancer patients by buffering one of the ways in which negative effects of nitric oxide are produced. And that, of course, was peroxynitride, which is a highly reactive, highly oxidative compound. And we can stop its negative, or at least lower its negative consequences by having good antioxidant profiles, by having good nutrition, by having good glutathione production and recycling. And of course, we know that for glutathione production, we need sulfur and protein. And for its recycling, we need a good, healthy mitochondrial metabolism, which incidentally is also the second, function of methylene blue that we wanted to replicate, which we can do by abstaining from carbohydrates because they are fermentable and they actually suppress mitochondrial function. Carbohydrate metabolism suppresses mitochondrial function, and by removing carbohydrates, we now are left with an energy void, which we will fill with fat, because fat can only be burnt in the mitochondria, can only be metabolized for energy in the mitochondria, and this promotes mitochondrial metabolism whilst suppressing cytosolic fermentation, especially in those cells that do have mitochondria, and we will leave the system intact. In generality, we will have general better health, and we will replicate the positive effects of methylene blue without incurring the negative effects. And I think that's very, very powerful. I think that's very, very valuable, especially because this allows us to get the positive effects of methylene blue chronically without incurring the negative effects chronically as well. And If you found this information helpful or interesting, I highly encourage you to like the video and share the video. If you want to know more about what we do, again, go to marchwood.com/outlive. If you want to read about our methods, go to marchwood.com/mosaic or just marchwood.com, where we have a lot of articles. And of course, check out the article on specifically methylene blue and nitric oxide in the description below. With that all over the way, swift healing to you, lasting health, and God bless you.